102 slides. I'm happy to take interruptions if they're not going to be too long. Anything explanatory, questions, confusions, please. And I like interactions. So I encourage that, but I do want to kind of make it to the final slide. So thanks to everyone who was involved in inviting me, thinking about maybe having me come talk. I haven't been here for probably 10 years. That was cognitive science when Paul had invited me a long time ago. I've been working for, I guess, about 5 years now on trying to address some of the sort of fundamental semantic issues of communicating with computers and, by virtue of that sort of proxy element, to robots. And I'm not a roboticist. I'm completely ignorant with the real hands-on robotics, but I like talking to roboticists, and I would like to talk to robots. What the work I'm going to talk about here, it's been funded by a couple of programs, one within ONR, one within DARPA, the Communicating with Computers program, which we've been working on for 3 years, and also some NSF work. And so I am going to talk about simulations and the role of simulation in communicating between humans, but human to computer, or avatar, some kind of agent, and then eventually to robots, to physical agents. In order to do this, one of the fundamental issues is to understand what we share in our interaction. And that's this notion from philosophy and psychology of common ground. So I don't want to adopt a kind of airy-fairy, flaky notion of embodiment or common ground that might be useful for a paper. We need to actually operationalize it and make it a formal data structure. So we'll get yelled at by the semanticists and the philosophers and the logicians to a large extent, but probably from the roboticists too. But we have to be practical and useful in order to operationalize what we're doing in order to communicate a human to an agent of some sort. I will have a demo. Well, it's a video. It's not a full demo. It's just a video of a demo of one of the interactions between a human and an avatar agent. This is the general kind of setup that we've been working on within the context of the CWC program, the Communicating with Computers. In order to talk about communication, one of the goals that we've been promoting in our effort within that work has been to have the computer basically show its cards as much as possible. Namely, to demonstrate as much as possible and as transparently as possible to a human user what it understands about a situation. Not to spew out the current state description as 1,500 literal sets and axioms and then do some sort of satisfiability, but rather to envision, to simulate what the machine thinks about a certain situation as much as possible. To visualize. In other words, to simulate. To that end, we've been using the Unity gaming platform to create a 4D model, to do model generation, just as in computational logic, minimal model generation, but we've been doing minimal model generation to create simulations. So here's the setup. I have someone whose name is actually Raul, and the current avatar here, Diana, lives in a virtual environment, and Raul lives in Fort Collins, Colorado State University, and they're basically tasked to build something together, cooperatively. So there's a communication that needs to go on, and they need to essentially cooperate to build a very simple structure out of blocks. We're talking about blocks world environments just to keep the domain and the inference set from blowing up exponentially, as well as just for planning purposes. So there's two scenarios, and what I'm going to talk about today is the one scenario. The first scenario is that Raoul out in the real world has essentially a big screen and can see inside Diana's environment and can point to anything within Diana's environment and can talk about anything. And she has a synthetic vision using a series of connects and can see where he's pointing and can also see where he's gazing and also knows what he's talking about if she understands the utterances appropriately. He will ask her to do certain things like move blocks, shove blocks, lift things, pick things up, things like that. They'll engage in a dialogue. The flip side is she sees what Raoul has out in the real world and will point to those blocks herself and have Raoul move those. She'll see those through the vision system and acknowledge that that was the right thing to do or to undo, to correct, et cetera, et cetera. I'm going to talk about the former situation today. Okay? So that's the dialogue situation. That's the cooperative, peer-to-peer communication in order to achieve a goal. Any questions regarding that? That's all I'm talking about today. Very limited. All right? Not at all bringing in the presuppositions, the accommodations, the bridging phenomena that people talk about in computational linguistics and computational pragmatics and discourse and dialogue. All these incredibly interesting and necessary things for most human-human interaction. I can't talk about those. That's just too rich a set of assumptions. We're going to start really slow. So we're basically, if we're biologists, we're starting maybe not even with yeast. Okay, but this is a yeast model. Maybe someday we'll get to Drosophila, okay, or C. elegans, but this is yeast. All right, so here's the questions addressed. How do we communicate our thoughts and intentions and our wishes to each other using conversation in a multimodal fashion? So this notion of competence, which is a bugaboo word in linguistics, is the production and interpretation of expressions, but it involves mental representations that denote the content of my utterances and my intentions. So what we're going to do in this approach is to create a framework that we would hope other people would share in. And it's not just our work, which is the best work. Well, it is now because it's the only work. But I want to have the framework itself be what would be adopted, all right, as a way of examining a problem. And so for how to interact, how to study interactions and communications, mostly in embodied communication involving multiple modalities. So embodied communication, we're going to talk about defining, but we're talking about dialogue. What is the notion of a shared experience? How are we going to define common ground? Okay? So one of the first things that we're going to notice, even with very simple interactions between our human and our avatar, is this notion of a disembodied reference, where I'm pointing to something or I'm referring to something, and it's been disengaged from an alignment of a couple of channels of speech and gesture or gaze. And I'm just referring to something as a word. And we're all of a sudden able to recognize that I say block, and I mean that block without pointing to it or gazing to it. How do we do that? This is, from a learning point of view, an extremely difficult problem. And there's a lot of computational binding going on there, which we'll handle through our procedures using continuations and state monads. But how humans do it is a matter of experimental question. But this notion of disembodied reference. So here's the basic thing in most communication between conspecifics, people of the same species, is that they actually have no common ground. The common ground isn't there. You're talking about things that happened to you when you were hiking in Yosemite last week, and you're describing El Capitan, and your friend's talking about the storm that was happening back in Boston. You weren't there. But all these things are basically understandable by virtue of, obviously, millions of hours of past experience, but the way we're forming and creating simulations of what you're saying. So in Alvin Goldman's notion, you're mind reading what somebody's saying by creating a simulation. Okay? That does, in fact, relate to mirror neurons and the mirror system hypothesis. Rizzolatti and Arbib and others. But I'm not going to talk about that today. That's a different paper. So the idea is that words and phrases act as proxies to being embodied, what I'm going to call a simulated embodiment. So I can show you this, or I can just talk about a watch. I didn't have to show it to you. The word watch creates a simulated embodiment. And you're going to visualize, you're going to come up with some sort of model of that. You're doing a minimal model generation of watch. Maybe not this particular one, but something that's more familiar to your own experiences, whatever. Now, in joint activities, Jason.
So when you say minimal model generation, are you going to say more about
yeah.
model should be minimal?
And what we mean by minimal, yes. So I want it to be just minimal enough and not more minimal such that the watch is going to be identical to my belt and to my shoes. Yes, no. It's going to be minimal to satisfying the particular creation of a particular form in a visualization.
Does minimal mean underspecified? And could the underspecification be handled by, say, a probability distribution over classical detail?
That's exactly what it means. Yes, yes. So to just take that point, if I wanted you to think about, imagine a dog chasing a cat up a tree. There's a lot of stuff you can leave underspecified, right? But there's going to be a relative placement of the dog and the cat. You're going to have an orientation of some sort of vertical projection, a cylindrical form, which you're going to create as an abstraction of a tree. Why? That's probably what you did. Are there leaves on the tree? Maybe. What color is the cat and the dog? Those are underspecified variables. How far is the cat from the dog? Probably close enough to be of some concern, right, to the cat, or to be of some interest to the dog. But there's a lot underspecified. That's minimal model. Okay? Any other questions regarding that? So we're going to focus on events because shared experiences and tasks are all events. And so I'm going to have to talk a little bit about the event modeling protocol that we have that goes into a dynamic logic, which then gets translated into C#, which turns into Unity as an actual rendering. But that part we're not going to worry about. Now, I won't necessarily focus on this issue that relates to language evolution and the issue of recursiveness, recursive structures versus non-recursive structures. But if there's interest in this in discussion period, if we have any time, I could talk about recursive disembodied references, which I think is the signature, the hallmark to human communicative behavior compared to non-human communicative behavior, which is the ability to recursively refer to objects that are disembodied as opposed to just simple recursion, which arguably is a behavior present in many non-humans. Now, DARPA has, over a couple of programs, but particularly within CWC, outlined what they call hallmarks of communication for evaluation purposes. This is not something that Pinker or Chomsky would agree with. But this, operationally and for evaluation purposes, this is what the community within CWC agreed upon. You have to have the ability to move a conversation forward. You need to be able to make appropriate use of a lot of different modalities. And we'll talk about that. You need to have each interlocutor be able to manage and manipulate and direct the course of the interaction. And you need to have both parties to directly and clearly reference objects in the interaction based on different frames of reference, right? Relative, absolute, and then, of course, intrinsic, right? The front of my computer is different than what the front of the computer that you're seeing, right? And then we need to be able to acknowledge and then demonstrate my knowledge of the changing situation. So we have a dialogue manager, push-down automaton, not an FSA anymore. We need to make appropriate use of different modalities. We have a machine vision. We have a synthetic vision from the avatar's perspective. We have language, and we have gesture. We have a small bit of gaze that we've integrated. And we can steer the course of the interaction. So the human can direct the avatar towards a goal. The avatar can ask for clarification, can teach the human what she understands. And it can go either way. We have what are called ensemble references using pointing, small elements of language, and then frames of reference that we can determine on the basis of constraint satisfaction which frame of reference are you referring to. My relative frame of reference or your relative frame of reference. And then we visualize the epistemic state of the agents with an epistemic visualizer that we call episem. And I'll show you that. It's still in development. Okay, what is common ground? And if I'm going too slowly, and you've already heard all this stuff from the previous lecture or something, just raise your hand and say go faster. Well, prosaically, it's just the ability to understand another person in a shared context, right? And then there's the big item terms are co-situational, co-perceptual, and then we've got other things like co-intentional and co-attentional. But the things that we use are these anchors. They're actually tools. They're channels, whatever we want to call them. They're massive computational devices, but they're just anchors for now. They're language, so I can talk. The clock at the back says 11:25. Okay, that's probably right. That's probably wrong, actually. It hasn't been changed to EDT yet. Gesture, that clock is wrong. Okay, I can gaze at it, you'll look at it, and I can make an intonation that will be a question, or I can do this kind of whatever. Intonation can... So we're actually experimenting with an intonation language that doesn't have any content, just using grunts and intonation to kind of model sort of primate vocalizations with gesture. And there's actually quite a bit of information you can do with just that. So we're going to talk about a common ground structure, which is kind of like a record type, if you're familiar with Robin Cooper's record type structures. And by extension, if you know Lapin's work and Lapin's associates and Ginsberg and others, you can make a probabilistic record type structure. Okay, so the reason I like this is that you can come up with a basic structure called a situation. Right? We have a situation right here, people, and we are all part of the situation. So I can identify the conspecific agents engaged, the shared belief space. That's going to be large unless I take a very simple yeast model like blocks building towers. The objects and relations that are jointly perceived in the environment. That's not so big. That's actually pretty small, depending if I don't take like second order and third order relations. And then the embedding space, very important concept. The embedding space that both conspecifics embody in the communication. So we'll talk about this, but embedding spaces are really important for defining how I use something, how I perceive something, how I determine that you can use something, that you can do something. And it's going to be the precondition from which then I can then determine whether some Gibsonian or other types of affordances are even going to be relevant to you. So let me take an example. So, and if I'm going again in too much detail, just let me know. So the embedding space for this talk is the auditorium, right? But the people in the front row have a sub-regional embedding space than the people in the back row, okay? And that's important because we want to know that because they're facing me. You guys can see those guys' backs. And so on and so forth. So there's a layering of embedding spaces, and there's individual point-wise, pairwise embeddings, or 3YA, right? We can create little graphs and clicks and stuff like that. Those are all different embedding spaces that may become relevant depending on what I want to do. And gazes and deixes also determine embedding spaces by virtue of creating a vector array or a vector cone, and I've got this, what are called tunnels, and tunnels in GIS, right? In annotation schemes for GIS, a tunnel to the person right there, that's an embedding space, all right? That we're sharing by virtue of certain action. Okay, this will be important. So I'm going to put this all into a box, and this box is going to be called the common ground. So this is going to be the presuppositions, and I'm sorry, this is kind of rough to read, but it's basically just an utterance that says you see it. And those things are going to be indexed to the things in the common ground. Now, I can share an experience by situating and being situated in it and perceiving it, right? Now, that's different than having shared actions. Because you're just sitting around and it starts raining and you guys are just, you're both there out waiting for a bus, and you're sharing the rain, right? You're sharing getting wet, but there's no action. It's just raining. So that's a very different type of embodiment and situated, co-situatedness and co-perception than if we're actually co-intending to do something and co-attending at certain objects. So we get the distinction, right? Attend to and intend to do something, right? Okay. So, and attention, it's not an event-object distinction. I can attend to an event as well, right? So it's polymorphic. Attention can be, I'm attending to the lecture, but I'm intending to make a really difficult question for this guy because I don't agree with him. So then there's shared situated references. That's the things here. So everyone, I can see your color of your shirts. I don't know what color pants you have, but I assume you have pants, and shoes and things like that. So there's all these presuppositions that are not part of the perception, but are part of the general belief system, the axiom system that I would hope to have associated with that. All right. So let's talk about events. So the way we experience events, of course, is different than the way we talk about them. But language is richer than gesture in allowing us to package and quantify and measure and order experiences. Gesture can only do so much of that. Now, and I don't mean artificial gesture in the sense of the construction of a sign language. And don't take me the wrong way when I say artificial. What I mean by gesture is a sort of natural gesture that would emerge from primates, but also co-speech gesture and co-gestural speech in kind of natural dialogue. Okay, not something which has its own complete semantics and syntax as sign language. Now, so language and gesture are going to be the things we're going to focus on. So communicative acts, we would probably agree, are going to be composed of informing, asking, telling people what to do, and then other things which are harder to do with gestures, actually, and are also a little bit less present with in the primate community gesture literature, such as warning and inviting and promising. Although warning, of course, is one of the first gestures you're going to get in primates. But let's just look at these types here. So they break into two types, kind of like feature structure values. You have atomic communicative acts with like warn, invite, and Greek, and the reason they're atomic is that they're directly interpretable actions which reference the agent, or perhaps the agent and the interlocutor, but there's no complexity to it. Complex acts are operations which are over-embedded expressions which are themselves interpreted. Okay, so I'm going to promise, but I'm promising something. And what do I promise? I can make a very simple gesture like, I promise, and it's from the context what I'm promising, right? You lap it up from the context. Move that block. I mean, that's a very complicated expression. It's an imperative, but I've got to dig down and figure out what the event is. Yeah. Yeah.
I'm having a hard time thinking of warning as atomic. Imagine if we were out in a golf course and I'm pointing, just pointing and saying, watch out. It's probably a ball flying at you. So how does that not involve?
Yeah, that's a good question. I would probably change the type. I would make it more complex. Yeah. I have no investment in warning being atomic.
So you're thinking about warnings that don't involve something other than the
right.
Atomic, but it could involve some gesture.
Yeah, no, that's fair. Again, no investment in the specific value, but rather to come up with a taxonomy that is functionally but then operationally important, distinguishable. So
in that case, it would be more of informing in the sense I'm informing with alarm that there's something coming.
Exactly. So, for example, in the gesture recognition system that we use from Colorado State, that's Bruce Draper and Ross Beverages. They've got this 11-layer CNN that does 30 different gestures. You don't necessarily need to know. You could probably get some of these just on the basis of the features coming in from and the analysis of the 11 layers, right? But the complexity of the interpretation of the specific gesture would not be. But that your point's very well taken. Okay, so let's just take a communicative act to be this tuple that associates with the modalities available to the agent involved in conveying the information, right? And I'm just going to focus on 3 forms, but actually most of the work we're going to be doing in the demo video I'm going to show is actually going to be the combination of some speech and some gesture, okay? So for every one of these configurations, and you could add them, including gaze and, well, action, actually, and then maybe haptic or proprioceptic information, which might be really important if you're trying to model the communicative act associated with having a robot put on a gown in a hospital setting, right? Those kinds of things, those types of interactions. That would also be applicable here. That's the type of interactions we're thinking about. So an assistance to patients in assisted living cases or hospitals, right? Where you're really trying to take in kind of proprioceptic and haptic information as well. Although we haven't studied that, but we have talked to people doing stuff like that, like Matthias and Jivko and others. Yeah.
This might be a minor point on the previous slide. First of all, when you say a tuple of expressions, I might imagine some alignment between the expressions also.
Yeah, we'll come to that. Yeah, we'll come to that. We have absolutely, that's totally underspecified, and that will not actually be a formal characterization of the act. Yeah, yeah. That's a very good point. So we know events pretty well in terms of a lot of features that help distinguish the shape of an event and its kind of its density, and a lot of the discriminative characteristics of events have been studied for probably 80 to 90 years, and we've got a pretty good sense of what you might call the look and feel and shape of an event. And it involves whether something lasts, does it change? That's durativity and dynamic. Does it have a kind of natural completion? Is it point-like? I can talk successfully and finish my story in 10 minutes or an hour. That's a telic event. I can be cut off short because I run out of time, so I'm abruptly ended. You can just all of a sudden fall over or just die of a heart attack. That's something that, certainly a change of state, not a very nice one, but it's not a result of something that I was planning on doing, right? So these break different types of event types. These are the categories that if you had an event classifier that you'd want to train, you'd want to basically find states, activities, accomplishments, achievements, and what are called semifactives. Semifactives are these little point-like things like wink or knock or cough or laugh. And usually we don't just have one of them. Much to people's chagrins, the guy in the back is usually coughing a lot as opposed to just one cough. So that iteration of a single point-like thing makes it a process of coughing. So these are very important things to recognize if you're trying to recognize events too. And robots and, of course, event and activity recognition software needs to make such distinctions as well. So events can be described by gestures to a large extent. There's a syntax that comes from the gesture literature. I'm adopting Alex and Matt's version of it, although they didn't create it. And it comes from the 80s and 90s. I have the literature at the end of the paper, of the talk, if you're interested, where a gesture can be seen as a preparatory phase, optionally, a pre-stroke hold, and then a stroke, and then a retraction. Do you have a question, Jason?
No.
So that's basically, I can have people here probably know gesture. Some people know gesture better than I do, but you can kind of imagine just from the name what these are. And the content-bearing phase is going to be the stroke, okay? And that would be like the deixis, the actual demonstratum, the pointing gesture. And gestures can denote quite a range of primitive action types. So grasping, holding, picking up, moving, throwing, pulling, pushing, separating, putting together, not to mention other things like that. Things which might be scalar, like this, okay? And so we're working with some turtle bots to basically have them do that. And I don't know if you heard about the failed Amazon drone that was reacting to some gestures that go this way, to go that way. So yeah, it's a huge area, and our work in that is, of course, very trivial compared to the larger companies, but we're interested in the dialogue and the communicative aspect of it more than the actual gesture. So let's think what a gesture grammar might look like. So deixis is going to be this pointing, and it's going to have a direction, and it's going to be directed towards some object. So I'm just going to make this very simple little tree, and then I'm going to basically have it go to a specific demonstratum, and this is going to go to a specific individual instant, a constant, some object in the domain. Okay? And then I'm going to introduce another yep.
If B1 was a location in that common space, would you still consider it deixis?
Yes. A very good question. I'm going to talk about that. Yes, so that is the big problem as you probably know, in deixis, is am I pointing to the table or to the location above the surface of the table? Am I pointing to that location or the object that's in that location? Yeah, that's a very good point. Then I'm going to define something which is a slight extension of Gibson's notion of affordance, but it's to my own use, where I'm going to talk about an affordance being an action and a specific object. And notice that it's just an action, okay? There's no subject. There's no subject. The subject is completely contextualized, all right? It's like there's no subject in the language because I can't talk about you doing that. I'm talking about just me, okay? So let's put it in the common ground. So I've got my common ground epistemic domain delta. I've got this individual B1. I'm sorry if this is hard to read. And here's my little pointing, and I'm going to a specific direction, and I'm pointing to that specific thing. Okay, so then an instance of that might just be that. Okay. Now, gestures denoting affordances would be things like grabbing, pushing, throwing, and what is implicit in the grammar in order to get the interpretation, to get the semantics right, is you need to embed it within an imperative. It has to be the person who's actually going to be doing it. So if I'm conveying to you, I have to impose the person who's doing the activity. And notice that if you can read this, there's two things going on here. I have the conspecifics in a complementary structure. The person saying it is A2, and the imperative is A1. So imperatives are by definition outwardly directed. Okay? Now you can imagine talking to yourself and telling yourself to do things. Like, don't do that. Don't do such stupid things. You're talking to yourself. But you're talking to yourself as if it's the kind of, I was a second person. Okay? And that's been studied in psychology. So now let's put a couple together. So what in the literature is called a gesture utterance, which is kind of like a sequence. This is a sequence model of gestures. So I'm going to have a point followed by an imperative affordance. So basically what I'm doing is something like, okay? And now that will work. Now your question is now very relevant. If I have a blank region and I do that, that's not going to have a value. It's not going to interpret unless I want you to go and kind of grab the whole area as much as I might be able to determine it. But what's interesting about this is if I do have a well-behaved domain and I've got an object in that region, then what I'm actually having to do is to do a co-reference to the value of this B1. Because why? Because the second gesture has no reference to that object. All right? It's just the gesture. So it's already this underspecified representation, which is actually in our semantics is a continuation. So this is a continuation, and this is a continuation, and I have to do composition to basically get the binding to work appropriately here. And that's actually however you do it via continuations or delayed binding. It's a fairly complicated act. You can get it more complicated, and this is what very typically happens. So that, and now your question comes in. So basically, I'm taking an object, and I'm telling you to move it to a location, which may be empty, or there may be something that I want to put on top of it. So deixis, we'll have to look at the semantics of deixis. So notice one is an anaphoric relationship, and this is a cataphoric relationship. And that absolutely demands a kind of continuation semantics right here. I need to keep that open so that I can go and then find, wait, what location am I going to find? I've got to go then suck it up with the next gesture, the next word, the next gaze, something from the context. It doesn't have to be a gesture, okay? Something in the common ground will then fill that. That's why, when we get to it, you'll see that this entire, you asked about alignment, the entire aligned ensemble is actually something that has to be continuized, because you need to be able to access any variable in here as being able to fill that value. And I hope you can read this. It's still kind of fuzzy.
It's a whole lot better from a
Oh, is it? Okay. So let's talk about an ensemble. So an ensemble is going to be this temporally aligned common sequence of actions, gestural, speech, gaze, and other things. And so a co-gestural speech ensemble, as opposed to a co-speech gestural ensemble, is going to be, I'm going to take the top row to be essentially driving the syntax of the expression. Okay? This is important if you're familiar with the proto-language and holophrastic language debate of Arbib and Bickerton and other people talking about evolution of language from non-human origins. So let's talk about an ensemble in the common ground. I have my common ground variables defining my situation, and I've got a linkage which is going to be a fuzzy temporal alignment. Fuzzy is important because I can talk before I gesture, and I can gesture before I talk, and I can overlap. And the gesture may take a lot longer than just the word itself, so I have to make sure that I have some kind of give, and it can't be precise, totally precise. And this is my embedding space. Okay. So what I'm basically doing, and now I have an alignment. I'm saying that. That's the entire action. Okay. So I've got an ensemble of a demonstrative speech, which is aligned to this particular object, which was gestured, and then the second gesture has no language associated with it. I can continue. I can say that grab, and that's all I have. And you can make arbitrarily complex ensemble structures like this. Similarly, I can use a very simple typed deixis language of here, there, and do the same thing. See, that grab there. Okay, and I can just do that type of alignment. So we use this as the basic underlying data structure in the semantics for creating a simulation, which is to try to allow you to see what I understand and to demonstrate what I think the situation is. And this is in order to unearth the presuppositions that exist in communication. It's like bringing up the presuppositions. So, a formal model, such as a minimal model generation, is a really nice way to think about interacting. They enable inference, but they're not effective media for communicating with humans, because the communication is facilitated. A simulation is facilitated through semiotic structures that are shared and understood through both partners. That's why the visualization of this information is so important, we think. And also, we think that this is a nice way to represent what might be going on inside the brain of a robot before the robot actually does something. So let's get a simulation of what the robot is going to do if we're trying to cooperatively pick something up. You basically do a projective simulation of what the person thinks is happening. That's why we're doing counterfactual simulations that I won't have time to talk about. Okay, so in the simulation, concepts are types: linguistic, visual, behavioral, acoustic, haptic, emotional types. It's all a type system. Context is encoded through these modal ensembles in a way that I just told you. Multimodal objects are encoding types in intra and intermodal ensembles. So I can have a type associated conceptually in the ontology with a dog. I might have an acoustic element, which might be barking. I might have a shape, a geometry, and the activities associated with dogs, et cetera, et cetera. So context has no one prototype. Context brings in many prototypes for any particular type of object, of flying, of perching, of nesting. For artifacts, we've got conventional situations of how a pencil might show up relative to a cup. But that's one context of what its habitat might be. This is something in a drawer versus the actual activity of writing with a pencil. So the associated activity, which is an event and has a particular orientation and a configuration, which is its habitat relative to the agent, which is me. And all of these things need to be learned, but encoded and differentiated if I want to visualize and compose with other things to demonstrate my knowledge of something. So we need a minimal embedding space. We need object-based attributes. We need the epistemic condition on the object. And we need embodiments. I need to know how I fit in relative to everything that I'm manipulating. Okay, so let's just go on. So visualization is going to be a process which links each semantic object to a visual object enacted in a virtual environment, frame by frame. It's a discrete event simulation. And all these variables are going to be assigned, evaluated, and reassigned frame to frame. And then we're going to have a complete rendering of the whole simulation. So we need events to be dynamically interpreted. So in linguistics, we think of events as having sub-events. So like knowing is a state. Running and dragging has this little event structure. Transitions from being open to close. It's just a little situation calculus. Complex events go from there being no house to being a house. There being nothing in the glass versus a full glass of water. Things like that. Those are accomplishments. Now, this is work that I'd done a long time ago, but we've moved since to having a kind of dynamic interpretation of events as they unfold in time, and the objects and attributes associated with the participants being the primary component to the event. So think of cartoon strips. A state is just a simple frame. Transition is going to be just going from one state to another state. A process is going to be find an attribute, then just keep changing the value of that attribute. But you're staying within that attribute, like location. Okay, you're just moving. Okay, or size, or color, until you completely saturate a color or something like that. Those are going to be processes. Interestingly, something like an accomplishment is gluing two things together. You're going to take what's called a scalar change of putting on top, putting on top, putting on top, putting on top, and then at some point, it's a 10 stack, it's a 10 block tower, okay? And so from not being a 10 block tower to being a 10 block tower is a binary change, which is this guy, and it aligns, you have a unification with the thing right there. I call it the summer vacation with kids event. The kids in the back seat asking, are we there yet? Are we there yet? Are we there yet? Are we there yet? And then you're finally there. Okay. So you have these stacked layer of primitive constraints. And so from two events, this is the dynamic interval temporal logic, you can create the entire Venn-Larian event type system. And I'm not going to go into the details of this, but this is a multimodal logic, a hybrid logic, which we then translate into the unity system. And in this structure, it's the conventional interpretation of first order dynamic logic, where you have programs and formulas. And the most important thing is that you've got propositions that just sit here, and then it's going to be the same state unless some proposition changes. Okay? That's all. That's all you really need to know. So you have a dynamic event structure, which is basically a labeled transition system. I can concatenate states to be, I'm tired, I'm bored for 5 minutes, I'm bored for another adjacent 5 minutes, I'm bored for 10 minutes. Okay, that's a state. And I can create, so that's just concatenation of states. But you can take a label transition system version of this. I can go from being happy to sad, open to close, touching to not touching, EC to DC. Okay, so let's just continue. So this is just a very simple label transition system that we use as the underlying graph model. I can work along a particular attribute, such as a directed, such as a vector, an orientation, and go towards a wall. And so that will be a process, a directed motion process. So that's important for us to basically say, I'm going to change the location of my guy, of my object to Y, and then I'm going to change it again. I'm going to just keep iterating these things, and I'm going to eventually have changed the location enough such that I've changed it 10, 20, 30, 40 times. And then I can apply a test and say, are you touching the wall? So then I've actually moved it to the wall. Okay, this is how we learn using some neural nets, different types of event technologies. Okay, so let me just get through this. So this is a basic metaphor of change that can be used for, I'm just zipping through these. I can generalize this metaphor to talk about change in objects in general. So if I've got, I'm going to show you a little movie. I'm basically just changing the internal state. I'm doing a scalar change along the way, but at some point I'm getting to a new object, which is a table. So now I have a table. And that's just basically represented by this dynamic logic structure. Okay, now let's move on. So the habitat is an additional data structure that we need in order to model a simulation. This is basically encoding the information associated with an object. So the computer this individual is using the individual inhabits this space. There's what's called the affordance space between the user and the tool, which is the cone that affords the use of the screen. Okay, so if I'm at my computer, I am not here. I'm at, and at means using in the typical affording telic space. All right. So, and then the way I hold certain things for function versus giving are very different. So when trying to have a cooperation between a robot and a human for loading a dishwasher or whatever, I don't want to give the human the knife with the sharp end on, right? But I want to use it like that. So depending on what I hope to do with the knife and communicating that, the habitat is going to be different. I think I just moved my cursor. Okay, so affordances have two forms. One is a typical Gibsonian affordance, which is going to be, what can I do to this thing? I can hold it, I can grasp it, I can move it. But there's also the notion of what do I do with it? I can drink from it. So drinking from is not a Gibsonian affordance. Holding and grasping is Gibsonian. Drinking is a purposeful. The telos of this cup is to hold liquid so that I can drink from it. So we identify and distinguish those two types. Okay, so VoxML is this language that encodes these types of information. The event structures, the affordances, the geometry of an object, the programmatic information of an event, the functional information associated with an attribute. So it composes a lexicon called a voxicon. Each little VoxML type is a voxeme, and essentially is the beginning of trying to create a multimodal lexicon. So here's the distinction between Gibsonian and telic affordances. So here's an example of the attribute value structure for a cup, along with an instance of a rendering of a geometry. This is going to come from a sampling, from a distribution of geometries that we have in our library. The more representative, of course, the better. And these basically say that given a certain configuration of the cup, if it's in a particular orientation, I'm going to be able to support things in it. Only if it's in a particular configuration will it actually be a container for holding liquids. Verbs are going to be programs. And let me just go through this really quickly. Jason, sorry.
The affordances that you showed in that example looked like they would mostly have been inherited. Is there, so you have something saying...
That's exactly right. They'll be inherited from a container, yes. Yeah, absolutely. Good question. So now, here I am talking to you. Sorry?
Sorry,
Yeah.
another follow-up. So would you have another
Yes, for something with a mug with a handle on it. Other kind of cups that would have what other sort of properties?
Say a cup with a different color.
Yes, absolutely. In fact, you'd want to. This is the type of information you want to derive from a lot of sampling and arrive at that. Maybe get an assignment that I know it's a container, and then, as Jason said, inherit the basic structures, and then learn on the basis of the image features, the embeddings actually, to as much as you can derive those, what specialized features would inhere in this particular cup. Yeah. Questions? I'm just cognizant that I'm probably going too slowly or trying to cover too much. So now what we need to do is to know when what we're talking about is already known in the community and when I'm telling you something that you didn't know before. And for that, we're going to use a version of Van Eyck's public announcement logic, and something that we're moving towards is something like Eric Packwit's neighborhood logic. But right now, let's just take a very simple situation. So I'm going to model what we know as a modal operator. And so the 2 agents, the 3 agents, all of us here, we basically will operate over propositional content. And so the agent knowledge is going to be the set of accessibility relationships between situations. So this is a very nice way of handling the muddy children problem and other situations where I'm telling you something that you didn't know before. Okay, so put the red block onto the blue block, or there's a block you didn't see, or whatever. Anything that you didn't know. Now, so what this basically allows us to do is the conventional information in a modal logic that alpha knows phi, and this is basically saying I'm publicly making an it's publicly being made known by saying phi that, and now phi 2 is now known. Okay, so basically it's now public knowledge by virtue of phi 1. Now, it could be just by saying phi 1. But this is to indicate that by saying it's raining outside, you can infer that it's wet or something like that. Okay? Now, importantly, presupposition is entailed by the closure of what the individual agents know. So basically, this is the common knowledge. So phi is common knowledge to both agents. So so I can basically, we know that the lights are on in this room, okay? So that I don't have to talk about that. So if I want to figure out what to say next, I don't have to say anything about the lights being on. And if I say the lights are off, that won't be true unless something changes in the environment. So that's presupposition. That's epistemic presupposition. So here's the kind of things that you can do. Basically, this is the knowledge of the agent. So Diana knows the pointing gesture. The human knows that Diana is at the table. There's a presupposition of something. This is what's called assertion in the common ground. So given this information, I can assert psi. Okay? So the classic example of assertion in the common ground is to say, Bill's a bachelor. The common ground was that Bill had all the other presuppositional properties that would allow us to not talk about it. But I didn't know that he was a bachelor. Okay? I knew he was male, human. I knew he was adult, but I didn't know his marital status. Okay? So that was the common ground. And this is another esoteric. This is basically, given the presuppositions of this being the case, I want you to move the block. That's how you actually would, in this logic, make an imperative. Yes. This is unpacking the delta. Exactly. Yes. Thank you. There's going to be a lot of stuff like this, right? I'll show you in the episim some of this there. Now let's look at something called the public perception logic. In a public perception logic, what we want is to know, to be able to presuppose what we all see. And so this is any perceptual modality. Okay? So if we're all sitting on the ground, on the same ground in a field, ready to watch the eclipse, then there's something that's presupposed by our behavior and our co-situatedness that we're feeling the ground. It's a little wet. We don't have to talk about it, right? It's just common ground. So but you're getting that through the proprioceptive haptic interaction with the ground, right? Now, visual perception can be modeled by treating the vision as a modal operator for each agent. And then common perception can be seen as the presupposition that the closure over the agents seeing phi. So I don't have to talk about that tripod there, right? We all see it. It's part of the perceptual common ground. Perceptual common ground will then feed into, in most cases, some version of an epistemic common ground, propositional content. There's one other thing I should mention here is a coercion. Given that the logic requires propositions, I can't just see an object. I have to see that an object is there, okay? Or I have to see that an object is on a table. I can't just see an object. Everything has to be propositional, because objects are not going to be propositions, okay? That's just a hack. Okay, so the other thing that's kind of recursive about this is that in order to co-attend, two agents have to gaze towards an object or an event. Okay, so you have each one of those statements. I can see that you're watching something, and I can see that you see another agent see him. So you get this recursion, what in the 70s and 80s was the mutual belief recursion. But here it's just a sort of a very, very shallow recursive perceptual modality. Okay, it's not too deep. Okay, so here's some examples of public perception statements. Diana does not see the small purple block. Everyone sees that the red block is on the black block. The small purple block is not visible to everyone. Okay, so that's important to know. That's part of our state information. That's part of the common ground. As you said, we're unpacking delta. Okay, now what we've created is a way of viewing some of this, albeit somewhat clumsily. Jason?
That last translation looked wrong to me. Maybe it's not worth going into.
It is not the case that I can do transitive closure over the agents involved such that there's a purple small block.
But it might still be visible to everybody. It's not just that they might just fail to know that they're visible to other people. That would be a way of making that second thing true. Am I misunderstanding?
You're misunderstanding the semantics of the transitive closure. It basically gives you the God's eye view. But to say that the God's eye view isn't true isn't the same as saying it's not visible to anybody, which is a shallow. Oh no, that's a different operator. Absolutely, no, it could be visible to everyone except one. Yeah, right. And in fact, or did I miss what you were saying?
Maybe we should take it offline. You have a lot of slides.
Okay. Did you have a question too? No? Okay. So here, just a very rough way of basically saying in the language I've got gestures. I have some of the vocabulary that we're going to be talking about in our speech. And I've got some relations and attributes to objects. I hope you can read these. And here are some orientations. And these are going to be, this is what I'm going to be able to see and know in the context. And what's going to happen is you're going to go from pink to a darker shade to, I think it's blue, which basically is increasing confidence that something exists as part of my knowledge. So episim is this epistemic viewer, which has it models the co-agent in terms of its language, gesture, and the linkage between the language and gesture. Currently over just 3 domains: nominal, color, an ordinal domain of size, and nominal for directions. It also models the agent knowledge of perception and knowledge. Okay, so this is our architecture for what goes on. We have basically we do the parse through the communication bridge, which is this finite state dialog manager, and we bring in our VoxML resources from the library. We create the composition of those, which is a specific rendering in Unity. And I'll show you this in demo. So here's the way this looks. And let me now show you the demo.
Hello.
Can you hear this?
Guess what? The yellow block grab this? Should I grab? Yes?
Yes.
Okay. Do you want me to move this? Should I put the yellow block on the white block?
Yes.
Okay. What do you want me to grab?
The black one?
Should I grab the black block?
Yes.
Okay. What do you want me to grab?
The black one?
Should I grab the black?
Okay, let me just speed through. It goes through more and more. You get the idea.
Yes.
Okay, go on.
So what's happening is we're recognizing the specific region, and so the semantics. Or actually, let me just now go through some of the. So this is our dialogue grammar. The first thing that we saw was engagement, which presupposes synthetic vision of what she can see. And so the communicative act of engagement with no other words is basically just moving up like this. That's engagement. Okay, that's hi, how are you? And that's basically the semantics of that. It's sort of roughly, I'm here. I'm publicly announcing to you that I'm here, and I'm ready to work. So Diana will say hello, which basically indicates in the system, in the finite state system, me too. I'm ready to go too. Okay. So this is the point in the model that's being elicited. The pointing semantics of pointing is itself a gesture, but it has a reference. It actually has a specific content, which basically is to say find the terminus of the vector cone or array, depending on how we have a cone, and basically if there's no object in that, then take the region to be the denotation of that. Okay. So what's interesting is that a deixis by itself is already a very complex object. It's a container, and if there's something in the container, you refer to the container. But if it's just the empty space, then you take the region by itself. So the deixis can mean the object or the location, and we use it without fail, one way or the other, depending on context. So what happens in the semantics of pointing? I do this announcement of something being the thing that I want or I don't want. Now notice what happens. You didn't really see it because it was too fast. When she leaned over to pick up this block, she saw there was a purple block here that she hadn't seen before. So that introduced into her model, oh, there's a purple block. So she sees it, but then she doesn't see it anymore because she stands up again. So it's in her epistemic, it's in her knowledge, but not in her current visual view. Okay, so that's what we need to differentiate. There's disambiguation in pointing that needs to be resolved, that we take care of, and so on and so forth. I'm just going to walk through real quickly. And grabbing has its own special problems. Moving, what this is just show a little bit of the compositional interpretation that's going on using the step-by-step interpretations with continuations. I'm basically creating these lambda expressions that then get enacted to create the effect in the simulation. All right, let me just stop there. If there's any questions, I can go through specifics of other things. What I've been trying to argue for and get you interested in is a methodology for creating an environment for talking about common ground between humans, for sure humans, but particularly computers and, by extension, robots. And the idea is that by creating simulations, you're bringing up the presuppositions that inhere in a conversation that need to be unearthed in order to actually have an effective communication. And simulations is a great way to do that. It reveals what each party knows. And so it allows for multiple simulation generation as well. We create Monte Carlo simulations to try different options for what might be a good simulation of a particular starting point. And VoxML is this basis for this modeling environment. And we think that I think it's kind of an interesting formal model for capturing context and how to align the different channels of modalities or communication in interactions. All right, thanks for listening. Questions?
I had one in case others don't have it. I've answered them for it. Okay, let me ask. So in the diagram world that you're showing us the demo of, right?
Yes.
There was one sort of, I don't know what to call it, a combination of language and affordances, which, again, I remember when I was a little kid, I used to help my father with home repairs or whatever. So imagine, we had a Vespa, but imagine it was a car, and you'd be fixing the car, and you'd be under it, and you'd sort of stick out a hand and say, screwdriver.
Yes.
I'm a screwdriver.
Yes.
And then after a while, it's stick out a hand and say, pliers. You can ply.
Right. Right.
And then sometimes you'd stick out his hand with the pliers in it and say, spanner.
Right.
And I knew that I have to take away the pliers
Right.
and give him the spanner.
Right.
He never said. So that seems to be a second order thing, meaning in one imperative, I'm implying two actions.
Yeah, you are.
Capturing what Diana does. So if she has something in her hand and you say, grab something.
Yeah.
Would she know that?
No, that's a really good point, and that's something that we're enriching the model with right now. That's a great example where you've got a request, and then in the other context, you've got a request, but you're also making an imperative, saying, take this away, give me something else.
That's never part of the spoken request. It's somehow implied in the gesture.
It's implied in the gesture and the prior context, right?
Or I would think of it as the affordance, namely this hand can grab only one, two.
That's a good point. Yes. Sorry.
Well, it seems like there's some pragmatic reasoning going on.
Yeah, I think the pragmatic reasoning is probably facilitated by that comment, which is, I can only hold one thing. Take this out of my hand and give me something else, right? So, and that's probably the unpacking of the pragmatics, which is actually the actual physical manifestation of what the affordance possibilities are for this particular device, for this particular rig. Yeah, that's a nice example. I like that. Yeah. Well, see, Jason, what I like is, I mean, I think you're right. What I think is interesting in these types of investigations, experiments, right? I mean, we're doing experimental semantics, right? Is that you're kind of finding what's the origin of the pragmatic. So a semanticist will say, oh, that's pragmatic knowledge. Yeah, but where'd that pragmatics come from, right? It came from the actual physical constraints that inhere in the embodiment of how many objects can I actually hold.
Yeah, absolutely.
Yeah. I mean, I could have two hands like that, right? So.
But there's also a prior about what plans would be reasonable for the human capacity.
That's true too, and that's independent of the affordance structure. Yeah, that's true.
I mean, the speech in this case was pretty telegraphic.
Yeah, and systematic, right? Something that is kind of systematic, and you learn. Maybe the first time you heard that, you had no idea what he wanted, right? You know, but you learn quickly once you don't get dinner. Yeah. So currently, we're now moving into. Let me just tell you a little bit what we have, since you're not asking questions. We have. I have one graduate student, Dotuan, who is taking basically event capture data and learning different types of events and trying to learn the affordances associated with certain kinds of objects. And one thing that I'd like to do is for certain kinds of objects, learn how one would actually hold it or pick it up, which I know a lot of other robotics groups have been doing. We're learning from their work. We're trying to do it from a kind of semantics perspective while engaging with a human, using learning by observation and learning by description. Ben?
No one here is on C. Could you comment briefly on how you actually evaluate it? Does everyone get to propose their own site?
Yeah, so good question. we've been able to define our own protocols for evaluation, and essentially by going to those hallmarks of communication that I defined, right? And everyone has to have those answered eventually, who's performing. So for example, there are some groups that are working, interacting with musicians. There's some people who are making poetry and creating poetry with humans and automatically generated poetry, such as Kevin Knight's group, and they're evaluated in a completely different way than we are. So if we satisfy the criteria that we've worked out with DARPA and MITRE to a specific enough effect, then we satisfy the criteria for evaluation. And they increase every, of course, 6 months. We need to add these additional features. We need to be able to talk about a larger domain. We need to be able to be more proactive. We need to be able to have some presuppositions, things that are not there, references to things that are not in the common ground. That's one of our things that we're doing. Our next goal for evaluation, for what we want to accomplish in terms of milestones, is, I think I was mentioning this to Jason, just to learn certain kinds of concepts, like teach me what a row is, for example. So to teach Diana what a scalar object is. So you've got a two-dimensional, a two-hot point scalar object that has extensions on either end versus one, like a stack, versus a bridge, which is just a closed object, non-extensible. So even just learning an extensible versus a non-extensible object could be, I think, kind of interesting. Rather than doing it from lots of samples through lots of data, like learning with the neural nets, we want to do it interactively. So ask the person, well, is this a row? Is this a row? And try to understand without hacking it, right? Have the human interact to create the inductive bias, as we were talking. So that comes from the interaction through language, hopefully. Yeah.
It's kind of related to that, and also to what Sandy was asking about. So in the case where you have a constraint like moving as one hand, imagine learning that constraint, the pragmatics of that, just from a data-driven way, or you can have you put down type system, you have a state monad that only has space for one object and stored it at a given time.
Yep.
Is there a principled way for making a decision between whether you attack the problem from type system or machine learning, basically?
So that's an interesting question. So I don't really know. So what type of data would you have presented to you in such a case?
Well, I'm thinking about the data that I didn't consider the interactive work with the human and the
Yeah.
robot and the simulation
Yeah.
versus something that was just kind of a hard constraint.
Yeah.
Say, well, we're always going to have X number of hands, so we're going to have it as a constraint that we need to have segmented, for example. State monad is always going to be replacing whatever is there.
Yeah. That I don't actually know. That's a good question. I'll have to think about that. What's your thought?
I mean, honestly, the more I say it out loud, the more it seems like the type system approach seems a little hacky, like you were saying. I mean, it's putting it like
It would be a hack, sure. Yeah.
constraint.
You'd like to learn it, right?
Yeah.
But learn it under some sort of bias, right? Because you're not going to have a lot of data.
Right. Yeah.
So what kind of bias could you impose that would make it not hacky?
I mean, I just think from like a sparse distribution where you have to only get attend to one object at a time. If you're encouraged.
That's true. I mean, generalizable, that would be, so, okay, let's define a non-hacky constraint to be something that's going to extend over multiple different types of situations and learnings, and then let's say concepts. And that would be potentially something. So it could be orientation, it could be other things like you're saying, which would essentially be a sparse distribution. Yeah, I like that. I'll have to think about that. All right, thank you.